Witam wszystkich bardzo serdecznie na 17. edycji sesji Linuxowej. Na wstępie chciałbym podziękować wszystkim prelegentom, bo dzięki ich ciekawym prelekcjom znaleźliśmy się tutaj. Oprócz tego wszystkim organizatorom i ludziom, którzy pomagają w organizowaniu tego wydarzenia. Kolejno Fundacji Manus za wsparcie przy fakturach oraz Politechnice, która udostępniła nam salę, dzięki czemu możemy tutaj być. Więc chciałbym zaprosić na pierwszą prelekcję. Będzie w języku angielskim, więc so I would like to introduce Filip Drapejkowski, who will talk about deep learning and how it's used in sugar factories.
Hey, nice to be here again. So maybe just a few words about me first. So I've graduated this university, both my engineering degree and my master's was here. And I'm trying to do a PhD here like externistically, but it goes really slowly. And I usually work with computer vision problems, with neural networks, with machine learning. And I'm mostly focused on vision. Currently I'm working on autonomous driving for trucks, which tow trailers on the parking lots or yards in harbors. And I've been working with a lot of computer vision projects before. So, for example, in Mythic, they had a custom chip, so we did a lot of things to make the neural networks work orders of magnitude faster on low energy chips. So we were doing mostly pose detection models. So we were getting those stickmans out of people bodies so that we could use it for animation. I was doing some ADAS, so distracted driving, detecting people falling asleep behind the wheel, some things about detecting the vehicle ahead and the distance from it and alarming, but mostly the driver-facing camera related things and optimization related things and retraining the models, gathering data, managing labeling. In Ident, we are doing documents recognition. This is a fake document, just for the record. So it was at the time where OCR was not that advanced, so we had to detect each like text field and figure out which text field is which and recognize face, compare it to the pictures we had. Recently I've been doing a lot for food industry. So for example, there's a machine which separates, which cracks eggs and then separates white part of the egg and the yolk part of the egg. And sometimes it makes mistake, and the role of the algorithm was like to detect these mistakes so that they can be automatically filtered out. And some medical projects in Starmedia and in the student research club here in Politechnica, in this uni, and this was mostly medical data. So we've even managed to get the state-of-the-art tumor 3D segmentation algorithm presented in Athens in MICAI conference. Okay, so this talk is not going to be very technical because I think there's a lot of technical stuff already in the internet, which in good quality. So let's say I assume you know how neural networks work, or at least how machine learning works. But just in case, like a very, very brief simplified intro, just for our purposes, for purposes of this talk. Machine learning is a paradigm, a programming paradigm in which you show a lot of annotated data to an algorithm, and the algorithm walks through the annotated data and hopefully is able to replicate the annotation. So let's say we want the algorithm to detect people's faces position. So we draw a rectangle at each face on 2000 pictures, and then we put those 2000 pictures through the algorithm, and after that it can replicate this task. So instead of manually coding like if statements and rules, this is the paradigm in which we focus on data a little bit more, and we hope this algorithm will fine-tune itself, will bootstrap itself based on data. And some common tasks in computer vision with neural networks or other machine learning algorithms is detection. So that's the rectangles task, right? So for example, face detection. Segmentation would be like a picture coloring. So let's say you have a scene of a road, and each pixel gets a class, a color assigned. So if it's part of the road, then it's, let's say, gray. If it's part of a pedestrian, a person on the street, then maybe it's blue. And the whole picture is colored, so you know which area represents what. Instance segmentation is like a combination of these two. So let's say I want to have every person detected, so I have a bounding box, a rectangle around it, and I also want to know the borders, like where the person ends on the picture. Classification is like the easiest task maybe. So let's say you have pictures of cats and dogs, and you just want to know, is it a dog, is it a cat, is it pizza? And regression is when you want to predict a number. So let's say temperature, money, percentage of something, value of a house, just basically when you're predicting numbers. So I will only talk about the stuff I've coded or designed or managed or coded parts of it. So the project I want to talk about is big, so yeah, I will only talk about the parts that I know well. And I will mostly talk about what went wrong, because it is a success story, and the thing we've delivered works great for factories around Europe. But I want to talk about what was hard, what we had problems with, what was different than our assumptions, or what differed from the way we're trained. I mean, when I say we, I mean like data scientists or machine learning engineers. So yeah, so I just want to make a gloomy presentation of what was scary and how did we cope. And the tech leader in this project left the company in maybe early stage or half of the project, and so I was like promoted to the lead position, and then my manager left the company. So, and there was no new manager, and I had to do this both jobs, like leading and managing, and I had no training for that, so it was also hard for me. And I imagine this can happen to all of you at some point of your career if you're students. So here are just some lessons I got, so maybe they are useful for you if you ever decide to pursue like similar career path. So it's mostly going to be about communication, system architecture, maybe managing a deep learning project. Yeah, here's a list of people that were involved in the project. So a few things that we are doing. So this was a sugar factory. So we're trying to detect every single piece of sugar, every sugar crystal, so that we could count them, and we could say maybe this crystallization process went wrong. So maybe you need to melt all the sugar and you need to crystallize it again, because there are different sorts of crystals, fine crystals, normal crystals, agglomerates, seed crystals, and So the task was to get a good statistic of what percentage of good crystals are there and what percentage is bad. And it had 3 phases, so most of the time it was like on the top left, so everything was moving and we couldn't see anything. Sometimes it stopped, so we had to detect when it actually stopped and when it's like good time to run the detection. And there was a phase in which everything was crystallized, so the one on the bottom. So the optimal phase to make the good decisions. We were working with sugar beets, so if the knives were not sharp or misaligned, then this crunch chips thing would, yeah, it's supposed to be the lines, the fries, and if it's like the big parts like this, then the process is wrong and something has to be changed, or the knives have to be sharpened. And we worked with the actual beets, so maybe there were stones in there. I will get into like more details on beets later, but that was like the third thing that we were working with. Okay, first lesson. So we had to detect the sugar crystals and classify them into 7 classes. And we pushed it back to maybe 3 classes, 2 or 3, because most of the classes had no representation in the data from the client. And okay, what did we expect? We thought that we will learn from subject matter expert. So, you know, the guy that knows sugar, that works in the factory for 40 or 50 years or 30, I'm not sure exactly. So usually you expect this person will explain you everything about the data. If you would be doing a medical project, this person would be probably a doctor, a radiologist. We would codify it into a document. We will hire a labeling team. They will replicate some labeling that the subject matter expert did and that we did. We will get those labels, train the models, we're done. And what happened? So there was a lot of corporate issues. They couldn't allow us to have like an external IP on our labeling tool because of security. And so we were using CVAT annotation tool from Intel or OpenCV that it just transferred. We had some annotation guideline, and the subject matter expert was using something like GIMP. And it was really bad. We had some regular meetings with them, not regular enough for this, and they were sending us their GIMP drawings, and we are sending our CVAT drawings. But it was inconsistent, and when confronted with this multiple times, they admitted they just cannot label it consistently. So on the left, it's like our annotation on CVAT, and on the right, it's what we got from subject matter expert. Just an example. So a lot of time we were just transferring those drawings into another program, so we had, you know, this Excel sheet, and we've seen that we're basically trying to find a situation in which subject matter expert was inconsistent with himself, and it happened a lot. And finally, yeah, they admitted they cannot label it, that this data is not in a good enough quality to label it consistently, because as you can see, crystals are transparent, right? So there's a lot of them stacked on each other, and they couldn't place the camera in a different way because it was a big tank with high pressure and temperature. And yeah, and in machine learning, this you don't really get much better than the data that you put in. And there was one more plot twist. This really bad quality data, it was still much better than the real production data. Because the real production data was from beet and the clean crystals were from sugarcane. So yeah, so lesson 1. It's absolute priority to have the same tool shared with the client, with the subject matter expert, because well, we would come to the same conclusion: we cannot work with this data, but we would have this conclusion 2 months earlier. And if the data was good, we would need it anyway. And like, this is a prerequisite. Before you get common tool, you just cannot start project, and you have to push hard for this. And another good practice is just use a third company. Like, one company is delivering algorithm, one is, you know, the client company, and the third one is doing labeling. And then the responsibility is split, because you can focus on your job and the labeling team can focus on their job. So that's one option to tackle this, and nowadays companies do this a lot. Also, so they have like independent test set. And they were trying a lot to make this data better. They've put a lot of lighting sources in different colors, halogen lamps, LED lamps, different glass, but yeah, it was impossible. And we were in a pickle because we basically decided we cannot do this project. And another task was the bit slices. So counting slices like fries and counting disks, then converting it from pixels to millimeters. So for that we needed to know the distance from the camera, and we also needed a distance sensor, because the cut bit were forming like a pyramid, right? So some bit was very close to the camera and the perspective was different, and some was like, you know, 100, 150 centimeters from the camera. And this worked well. We inherited some code from previous team, we improved it, we got calibration, so we've put like a piece of paper with a grid, so we know how many millimeters are there in a pixel, we got the measurements, and the prototype worked well. So we were able to do like this. We didn't detect all the objects, but it was good enough to get good statistics. So they knew maybe from this factory in this part of year we have too much disk, so we need to sharpen the knives more often, or change something in the process, and this factory is okay. That's cool. What went wrong? They wanted to know which the situation in which the bits were frozen, and then they would melt down, but they would be damaged. So you can see the red lines from our expert would signify that this part of bit used to be frozen, and here on the right we have like normal crunch chips, and we're supposed to detect this. Okay, cool. So we've made a lot of algorithms. They were detecting it fine, but we've noticed a weird thing. There was a lot of frozen bits in June, in August. So the conclusion was they were just wrong. This pattern had nothing to do with bits being frozen. Like, their assumption was wrong. The whole task didn't make any sense. It was just independent to the process. So the lesson 2 is kinda, you cannot really expect the subject matter expert has everything figured out, and you have to always be vigilant. So the situation is bad. We have this project done, but the frozen stuff is frozen. The crystal stuff is frozen, and it looks pretty bad. So what we have done, we've proposed an alternative project. We went to the factory, because normally we were like working remotely, but we physically met those people, so it made better communication and better impression. And we were like, guys, you have so much things that are done by people and we could automate them. Maybe let's do something else. And they gave us like 10 pictures from the BitLoader, from the whole bits. And so we've crunched to evenings and trained a deep learning model with only 10 images to show them demo really quickly. So it's like this. So it's overfitting, so training and testing on the same data. All the best practices you can apply. And 2 days later, we showed them demo. Look, we are able to detect particular beats. We knew they want to know if the beats are dirty or clean. So we just figured if it's black, it's there. If it's like dark, it's covered with soil. If it's light, then maybe it has less soil. And it was good enough demo for them to actually commission the project. I will just look at the time. It was good. So that's the lesson. So maybe you can still deliver a lot of value, although it's different than all the parties expected. Yeah, and I don't have too much about it because it works fine. Okay. Another lesson. You can often hear that the golden standard in deep learning is end-to-end learning. So the less stages your pipeline has, the better. So let's say you want to recognize emotion of a person. So you just tell the neural network to recognize emotion from the whole picture. You don't actually detect the face, then get rid of background, and then pass it to the network that recognizes emotion. The better approach is to just put the picture in and let the neural network figure everything out by itself. Or at least that's the advice you will get from the biggest companies, the most recognized names. But this approach has limitations. Neural networks, at least the convolutional neural networks, have their limitations. The less data you have, like if you have 2,000 or 20,000 pictures, things work differently than when you have 20 million pictures. And the more end-to-end you get, the less debugging capabilities do you have. So if the model doesn't perform as well as you want, you have no clue why, because at this point, explainability of neural networks is not very good. So we did the approach that, okay. I think I ruined something. I'm not sure how. Okay, we're back. So they wanted to have percentage of weight of different types of contamination. So they wanted to know maybe 3% of mass of those sugar beets is soil, like dirt, right? And maybe 0.5% of the mass is leaves. 0.5% is molten beets, so you know, like there's mold and there's rot, and there were those beet heads. So the bad part of the beet was supposed to be cut off and discarded, but sometimes the supplier would forget to do it or cut cost and not do it. So like detect how big percentage of what we can see here is constituted by this but. And well, we've trained end-to-end regression convolutional neural network, and we got great results. And we were getting like 99% mean like between 1 and 0% mean average percentage error, and everything looked fine, and guys were like, okay, at least this part is done, we can focus on deployment. And yeah, there was a plot twist. I didn't trust this model at all. I didn't like the data. So I've created an alternative model, which was one-liner, and the one line of Python code, and the line was like return 5. So I just took a mean value, like took their annotation from the client, and like if, and I would return like 3.5% soil, because this was mean value, 0.5% leaves, because this was mean value. And guess what? My model was also pretty good. It had like 2% error. So I'm not sure if you get the situation. So it's like, let's say you hire a security guy, and then he figures for 10 years there was no break-in, so I will just stop coming to work. And for 5 more years there's no break-in, right? Everything is fine, but that's not what you were hired for. This model was totally useless because the training data was not diverse enough. So almost all the time it would have similar values. So let's say one day all the bits come clean or all are bad, and the model would probably not recognize it, or at least we can not check it. So it wouldn't be ethical to like deliver this model. And the labeling was totally wrong also. So we did a lot of data engineering. Like we figured we had like 20 different batches of data. We figured they had different labeling people. Some were doing better job, some were doing worse job. So we figured this and this and this part you should relabel. We figured like smart sampling, so we would discard a lot of data if it was repetition of, we would, the real distribution was like a Gaussian distribution with very small variance, and we would rather artificially pick data so we have a uniform distribution. So we have like almost the same number of pictures with clean beats and very dirty beats and, a little dirty beats. But it still didn't work fine. And like also the model had to like guess how much does it weight. And it was operating on surface areas, right? On pictures. So we did the whole thing from scratch. How? First we did instance aware segmentation of beats and leaves. Do I have leaves here? Yeah, maybe here. So you would get this line around each beat and line around each group of leaves. And then we would classify each beat separately. Like this was going to another neural network, a classifier. And it would classify into 3 classes: very dirty, slightly dirty, super clean. Head, no head, head, invisible, and partially cut off. And we figured that if we get the labeling, that the labeling people had impossible job, like guessing how much the dirt weighs. So they couldn't do this job well because it was impossible. But if they get picture like this and they're supposed to decide, is it very dirty, is it a little dirty, then it's much more reasonable task. And then we would train a linear regression in which we would, or a quadratic regression in which we would check the percentage of mass from the old labeling after all cleanup, and check the surface of each beat, like approximate each beat as a cone, and get this you know, algorithm which basically is one-liner that just computes the weight from surface. And okay, it has a lot of disadvantages. So now we have 3 different parts that can go wrong. A lot of work, no end-to-end training, so against everything you can read on like deep learning courses. But what we gained? We get debugging. Now if they're unhappy with results, or we are unhappy with results, we can check what exactly went wrong. So we figured segmentation is pristine, this instance segmentation. The detection of particular bits is almost perfect. The classification is pretty good. In the last regression, do I have a graph here? Maybe it's good that I don't have it here. At the very end, it was pretty good. So there's a lot of tension, and like people were starting to be like looking for culprit, like it's not working ideal, it's your fault, guys. And we were showing them, okay, this we have labeled ourselves, it works perfectly. This we have labeled together with you in multiple runs, it works fine. And the last part, it starts to work fine, and suddenly you have much more control on the process. You, yeah. So the lesson, I guess, is despite the fact it's so much more work, and it's maybe against the recommendation you can get from deep learning gurus, sometimes it's really good to have a lot of partial models, and maybe at the very, very end combine them into end-to-end. Just because in real life clients don't have perfect processes. Sometimes they have processes which don't make too much sense or need to be improved. And if you do it piece by piece, you can detect those situations and you can negotiate, let's improve your process, let's improve labeling. And at the very end, you get a great result, great model, great control. Yeah, I just will stop repeating myself and go further. And it also gives you modularity. So they figured they will totally change this, maybe put the camera 3 meters away and look at 25 tons of bits at once. So then you can reuse some of the modules. So that's another reason why end-to-end might not be perfect. Yeah. And the final result, it works in Italy, in Germany, in Ukraine, in Poland. They are super happy. It's scaled on production. They have those statistics and information. Which supplier is better, which is worse, which weather, how the weather affects these. Do they get like stones? Do they have rotten beets? So at the end, it worked just fine. Okay, lesson 5. One thing is to get algorithm working, and another thing is make algorithm work on large volumes on data, on production, and like deploy it. Our deadline was moved 5 months ahead because they had like some financial issues, and they figured, you know, the deadline was supposed to be 4 or 5 months from now, but now it's 2 weeks ago, or like my bosses canceled the whole thing. And we're crunching, and everybody is super stressed out. It's not what we agreed to, but we have to do something. But we were dependent on clients' infrastructure, and it didn't work. So distance sensors were maybe not installed. If they were installed, we had no connectivity. They told us the distance sensor is in Italy, so why no predictions? Well, maybe share with us like IP of the distance sensor as you used with the prototype, or maybe some, you know, password and HWS key so we can actually like connect to it, or maybe, you know, tell us that it's already connected. And it figured that inside the organization, they were hiring a lot of different contracting companies, and the communication wasn't working well. And like one party was giving us infrastructure access inside of the client's company, and another was, you know, wanting results from us, and we were working as a message passer between the two internal organizations in client company. And it was also super stressful, and my solution was we've created crazy big Excel document or Confluence document with a lot of tables. We called it requirements from production, and it's just a very small part of it. And we were like saying, this is working, this is not working, this IP is missing, it's the date of last status check, when do we give it to you? Well, 2 weeks after the requirements from your side are satisfied. Like the camera is installed, you tell us how many centimeters is from camera to the conveyor belt. And it was a good solution, because since we got this document, they were able to fix those issues because they could see all the issues in one place. They understood it's not like we're not working, we're just not getting the things that were promised, and like you want it faster, so go to the guy in your company and make him install the camera faster. And it took the stress from us because the responsibilities were clearly divided, and we stopped sending emails all the time. 15 minutes, okay, I'm almost done. And it also finally worked, and this helped. And maybe last note, the client always went for maximalist goals. And we knew, for example, we won't be able to give you 7 categories of crystals because you can only detect two or three categories of crystals, you yourself, and you don't have data that shows the other ones. We knew that percentage of mass is wishful thinking. How do you guess percentage of mass from 2D picture? We knew that a lot of classes didn't make too much sense because for 2 million pictures you would only get like 2 pictures with this specific class, but they were always going for the maximalist route, like 3 types of leaves, and they would never say let's do less. Unfortunately, it was like not a fixed price contract, rather paid by every month. And so first lesson is maybe, a sub-lesson is maybe, you know, iterate, like go with very simple goals, and once it works, then it's easy to extend it into more classes, but don't try to, you know, build, like, if you really want Agile, if you really want Scrum, just focus on small iterations, not on, you know, Jira and all the rituals. Small iterations are the most important thing, but the client wants everything maximalist, so we were like, okay, let's agree with them. Let's go with maximalist approach. And then when they see that they like cannot deliver their part for maximalist goals, but they also have more trust with you because they see how you work, how you communicate with them, that you know what you're doing, then renegotiate. So yeah, maybe that's the lesson that usually clients also need time to learn. We all do, and just give them this time. It's okay. That's it. So we have like 15 or 10 minutes more. So maybe you have questions, and I was told I have a T-shirt or 2 that I like these that I can give to two first people who ask questions. Are you planning on passing the mic, or? Yes. Yeah, thanks a lot. and Mr. Tomasz later.
Don't you think it would be easier to create an item in the line, in a conveyor?
Yes.
For like to check the quality and not depend on the infrastructure at all. Just you put an item which you develop and like no communication needed. Like because probably it was a main issue from as I
so like here, if the conveyor belt would be really slim and there would be just one item.
Yeah, you can just have a line. You stop, like you take a photo, put all the sensors you needed at the appropriate distance, and get the.
Okay, yeah. So the question was if let's get a better camera setup, better line, better conveyor.
Like you develop a unit to test the quality.
Yes. Okay, even like a separate thing, like you take part of crystals, you put it into like microscope unit, they are in one layer, something like this. You basically not approach it from software point of view, rather make all the setup better.
I mean, like you know the process, and they have like a line, right? They like producing the sugar, and you create your unit to.
Like physical unit we ship to them. We suggested things like this a lot. They weren't ready. They had their own process. They have those machines. They have hundreds of these machines already there. They are in the field. The camera is in the field, like, you know, far from civilization maybe sometimes, has to work offline. And they were not open to changing this. We were suggesting something like this, maybe something like, maybe not shipping the physical device, but rather changing their process. They were insistent. You know, maybe other team is now continuing the project. Maybe they will change mind eventually. And it's a good idea, and you're right, it would work better. But they didn't accept this idea. And we had deadlines already when I started to like make decisions, and I had to squeeze into those deadlines and budget constraints. So, you know, if I only had like 5 months to finish shipping physical devices to 4 factories, it was just not feasible. But you're right, it would work better. Tomasz, right?
1, 2, 3. Is it working?
A question regarding both the crystal part and this conveyor belting. How about better lighting, colored light, polarized light, some filters, because these pictures looks kind of crappy?
Yes, we spent a lot. Okay, so we couldn't, like, we weren't manually going to the factories. We had no budget for that. But we had a guy that was from the client side that was experimenting with it a lot. So for the beats, they just told us the conditions will change a lot. The angle of camera will change a lot. There's some cover for sun. There's some LEDs, but they can get dirty. And they just told us it has to work in crappy conditions. That's it. And it worked fine. At least actually the beats, it worked really fine. And for slices, it also worked fine. The problem was like labeling. But with crystals, they spent half a year trying to make it work. They have put halogen lights, LEDs. The problem was that it's a big tank with camera attached, and some light sources and even a camera just melted because the room is very hot. They cannot put anything inside the tank, so there was a lot of physical limitation, and the guy was wearing not hazmat suit, but a lot of protective gear to just go in there. So you're absolutely right, it's a good idea. For, let's say we get the crystals in one line, so they are not on top of each other, and then consistent lighting, easy task. But unfortunately, it was not on the table. Any more questions?
this may be slightly off topic, but did you have any contracts to, for example, automatically cut or montage videos using machine learning?
No, I didn't. I've played a lot with models in my spare time, but nobody ever paid me for this.
Okay.
Any more questions?
Okay, we're ahead of time. Thanks a lot. Thanks a lot for coming. So you two want t-shirts, right? Is that correct? Or have I overextended?
Yeah.
Aha, so we have two now. or you can, you know, you're speaking after me, so you can so you can give free t-shirts to people instead. You can reassign mine if you want, or yours. Okay.
Exactly.
Thanks a lot.
Yeah, thank you for the presentation. And we will have like 15 minutes break.